Thank you very much for your kind introduction and welcome everybody to my PhD presentation. I'm very glad that you're all here or tuned in online. Today I want to share with you the work that I did in the last couple of years. And the reason why I personally chose to work in power electronics is to help with the ongoing energy transition. So in 1960, there was the first observation of a steady increase of CO2 in the atmosphere by Charles Keeling. And after basically half a century of not doing much, we're faced today with the global climate crisis, with CO2 emissions being on an all-time high. And current studies already show that the future economic damages already outweigh the cost to reach the 2-degree target by a factor of 6. And as you can see on this map, the countries who are obviously least responsible for this will suffer the most. So you all know the agreements and that we have in place right now. For example, the Paris Agreement to limit the global warming to 2 degrees, or the European Green Deal to limit the greenhouse gas emissions by 55% by 2030. And this is obviously only achievable if we electrify all sectors. And as you can see in this diagrams here on the right, so the demand for electricity will substantially increase, obviously, especially renewable energies. And most of this electricity will be processed by power electronic converters on the generation side and also on the consumer side. And the main question is now how to satisfy this ever-increasing demand for power electronic converters. And one answer for this question could be an increased level of modularization of power electronics. So if you're a company, you already have markets, have products in the market, then what you could do to scale up the current or voltage is to take the product that you already have and combine them to have a quick solution for a new customer. And this has obvious commercial advantages such as lower development costs or also lower component cost. But it also has technical benefits because you can, for example, switch off one of the blocks in partial load and have increased partial load efficiency, and also have increased redundancy, for example. And in my PhD, I focused on galvanically isolated DC-to-DC converter systems. And those can be quite flexibly interconnected on the primary and the secondary side because they have galvanic isolation. And those types of interconnection are abbreviated, for example, in IPOP or ISOP, which stands for input parallel, output parallel, or input series, output parallel. And the main research question in my PhD was how to control such modular galvanically isolated DC-to-DC converter systems, because an interconnected converter systems is much harder to control than a single one. The main issues that I found in the current literature are that usually if you want to control such a modular system, all the variables such as power transfer, power sharing, and the state variables are always cross-coupled, which means that you cannot influence one of them without affecting the others. Usually in the literature, there's only those interconnection schemes that I just showed you and not more generalized or complex ones than those. Then usually in the literature, the control design is always done with respect to a very specific DC-to-DC converter topology and its operating principle. And last, usually the control design and the stability assessment is usually done based on linearized models and small signal analysis. In my PhD, I wanted to overcome this by developing a generalized control methodology that should allow fully independent and decoupled control of all variables in the system, that also should cover every theoretically possible interconnection variant, that should always also be completely independent of the converter topology and its operating principle, and that should have global and large signal validity. So in my talk today, I want to go with you through the following points. So first, I will talk about the simplest interconnected converter that you can think of, which consists of only 2 converters. Then I'm going to extend the whole approach to any DC-to-DC converter system that you can think of. And then I will talk about the experimental validation in the end before concluding and giving an outlook. So let's start with the simplest DC-to-DC converter system that you can think of, which only consists of 2 converters. And I will do this using a very specific application that you can already see in the picture. So a couple of years ago, a colleague of mine and I did a project on an onboard charger for a catenary truck, which is basically a battery electric truck, which takes its energy from overhead lines, which are installed on a highway. And those overhead lines carry DC. And because trucks are not well grounded because of the rubber tires, you need a galvanically isolated DC to DC converter to charge the battery. And the power rating here is 200 kilowatts. So we faced a particular problem at the beginning of this project, that we were faced with two different voltage levels. So on the test track installations, there were 600 volts installations, and for the highways, there were 1,200 volts planned. And to address this, basically, we came up with a solution of doing a 200 kilowatt converter by interconnecting two 100 kilowatt units. And to attach to the 600 volts, you can put them in parallel on the primary side, and to attach to the 1,200 volts, you can connect them in series on the primary side. And my task in that project was how to control this two converter system. So obviously, before you can control two converters simultaneously, you have to ask yourself how to control one of them. And yeah, the topology that we used is the three-phase dual active bridge. Most of you know it. And in this topology, all those semiconductor bridges are switched at 50% duty cycle. The phases are shifted by 120 degrees. And yeah, this basically results in those staircase voltage patterns across the transformer. And now if you introduce a phase shift angle between the primary and the secondary side, you can manipulate the voltage across the leakage inductance of the transformer. And this results in a so-called stepwise sinusoidal current waveforms in the transformer windings. For this modulation technique, you can find an equation, which is pretty nonlinear, as you can see. So the phase shift angle is basically quadratic in that equation. And this equation describes the current that is delivered to the secondary side of the dual active bridge. So because of this nonlinear equation, you would be ill-advised to choose the phase shift angle as the control input to your system, because then you would face a nonlinear system, which is usually quite hard to control. So there is a state-of-the-art solution for this, a linear open-loop control for this converter, where you start not with the phase shift angle, but with a commanded current. And the first thing that you do is you take the inverse of the equation that I just showed you and calculate back to a phase shift angle first. Then you take an algorithm called ICC, or instantaneous current control, which was also developed at this institute like 10 years ago. And this allows for this secondary side current to be established in a very, very dynamic way without generating a DC offset in the transformer windings. So you're basically using this approach. You start with a commanded current and end up with the actual hardware producing this current very dynamically, except for a very small error. And this basically makes the three-phase dual active bridge behave like a linear, dynamic, and controllable current source. And now you can use that property to design closed-loop controls. And I already promised this will be the only control loops I will show you today. So if you have, for example, a voltage source as the load, then what you control is the current that flows into that voltage source. And the first thing that you do is you take your reference current and directly forward it to the converter, because the open loop control is already good. And then you can just basically take a measurement and use an integral regulator to compensate for the remaining error. And I did a simulation of this down here. You can see that this topology can follow a step change almost perfectly. And then at this point, I introduced a small error and saw how well the integral regulator could compensate for this. So if you don't have a voltage source as the load, so instead you have, let's say, a load resistor, then you have to control the voltage across the output side DC link capacitor. And this is also very simple. You take the measurement, you use a very simple PI regulator, and then control the voltage. And in the simulation, you can also see here that a step change can be followed quite nicely. And also if you change the load resistance abruptly here, then also the voltage sticks at the reference value. So obviously it's very state-of-the-art and very easy to implement a closed loop control for one converter. And now the question is how to control two of them. And the scenario we looked at was the so-called back-to-back experiment. So in this experiment, you put two converters here in parallel, which I call A and B. And because you usually don't have a high power source or a high power load, what you do is run the power in a circle. And in this case, only the source has to deliver the losses to the system. And in such a setting, you have two control goals. First, what you want to do is control the voltage on the open and secondary side here. And the second control goal is, you want to control this circulating current. And the initial idea that you can now think of is, okay, let's just make one converter control the voltage, and let's make the other one control the current. And so what you do is you take the control loops from 2 slides ago and close one of them on one converter and close the other one on the second converter. And everything worked fine, like 2 slides ago. Everything was nice. You take the very same tuning for the controllers. And now if you do the simulation, you'll end up with this behavior. And you don't have to be a control engineer to see that such a behavior is not very nice. You have all those oscillations here in the current, and also the current sharing is very bad. And now the question is, why do the same control loops as 2 slides ago behave so differently right now if you use them for an interconnected converter? And the answer is that now the plant is cross-coupled. I visualized that in that block diagram. I won't explain it. I will show it to you mathematically right now. The main takeaway is making any sort of interconnection will always introduce cross-coupling effects, and it's not possible to use the same control approaches that you developed for a single converter on a modular converter. So now let's try to understand this mathematically. So usually what you have to do is write down the state space equations for such a system. Most of you know them. I usually divide the manipulated input, which you can actively influence, with the disturbance input, which you cannot actively influence. And in this case, the state variable in the system is the secondary side voltage. The manipulated input currents are the currents that the 2 converters can deliver to the secondary side. The disturbance input is the load current, which flows through this resistor here. And the system outputs I define to be the terminal currents here of the 2 converters. And now you can derive the system of equations here, the state space equations, and you already see some problems here. So for example, in the first line, you can see that really both of those currents will influence the load voltage, which makes sense because if both of them deliver a current to the secondary side, they will both charge those capacitors. And the second issue is that, if a single converter here, for example, delivers a current to the secondary side, it will charge its own capacitor, but it will also charge the other capacitor, and this will cause a measurement on the on this sensor, and this will also cause a measurement on this sensor, and that's why this matrix here is fully occupied. And seeing that all those matrices are fully occupied basically shows us the cross-coupling, and this basically shows us that selecting those individual currents by the 2 converters as control inputs is not a wise choice of variables because both of them operate as a single unity. So now the obvious question is, what are better variables? The variables that I chose, I call the so-called common mode and differential mode currents. So the common mode current is the sum of the 2 currents that is delivered to the secondary side, while the differential mode is the difference of the 2 currents. And you can represent this by this transformation matrix here. And now, if you apply this transformation matrix to the input, then what you basically see is the common mode current describes the net power transfer from the primary to the secondary side. And therefore, this common mode current will charge the batteries. You can see this will charge the capacitors, which can be seen by this 1 here in the matrix. On the other hand, the differential mode current is the difference of the 2 currents, and because it is circulating, it will not charge any capacitors, and you have a 0 here. So you have already achieved decoupling here in the first equation. But there's even more. You can also apply the same transformation to the measured signals at the converter terminals, and if you do this, you will basically see that if you take the sum of the 2 measurements, you will basically just measure the load current and not the common mode current, because this common mode current charges the capacitors, which are actually before the location of the sensors. And if you take the difference of the 2 terminal currents here, then you can basically directly measure the differential mode, the circulating current, without measuring the load current. So also in the second equation, you have a diagonal matrix now and achieved a nice decoupling. And if you put this into a block diagram, this is what you basically see. And decoupled coordinates, now all those cross connections from the previous pictures are now gone. And you can basically take the measurement of the load voltage and use a voltage controller for this. And you can basically take the measurement of the circulating current and use the current control loop on this. And the final step is that you have to transform back to individual commands. And then if you do the control like this, with the very same controller settings as before, you have very nice control performance. So this basically tells us that modeling this system in common mode, in differential mode coordinates, basically actually captures the physical reality of the system, and those variables are much better than the individual currents. Are you still with me? Good. So now the question is how to extend this approach to any DC to DC converter system which is possible. So now the first thing that you have to do is do a little bit of classification. So first some terminology. When I will talk about the converter, I always mean a single DC to DC converter with a primary and a secondary side. When I will talk about an individual converter port, I will always mean either the primary or the secondary side of a single converter. And then you can take multiple of those primary sides, for example, and make a large interconnection with those primary sides, and then you end up with something which I call interconnected converter port. And then a whole DC to DC converter system will now consist of an interconnected converter port on the primary side and an interconnected converter port on the secondary side. So now let's look first at individual converter ports. And basically, these are representations of a power electronic topology. So in my PhD, I distinguish between two, which I called MC and MV type, where MC stands for manipulated current, which means that you have a controllable current source which acts on a DC link capacitor. And in this case, the manipulated current source here is the control input to your system. The voltage across the capacitor is the energy storing quantity, it's the state variable, and I define to be the terminal current as the system output. And with manipulated voltage or MV type ports, it's just the other way around. You have a manipulated voltage, a series inductance, and but for the sake of time, I will only talk about MC type ports today. So let's take one example, for example. This is a topology which is called a current-fed dual-active bridge. It's very similar to the three-phase dual-active bridge that I just showed you. It's only to fuse together with a two-phase buck converter on the secondary side. And as we have already seen, by using this open-loop linear control that you can also use for the single-phase dual-active bridge, you can actually influence the current quite well and quite dynamically. So you can use this if you solve this phase shift equation for the primary side current. You can basically make the primary side behave like an MC type port because it allows you to influence this current very dynamically. You can also solve the phase shift equation for the secondary side current, and this basically allows you to also make the secondary side make like an MC type port alternatively. In this case, these two load inductors have to be considered as part of the load. But what you can also do is take the voltage control that we have already seen, this is the same one, and control the voltage across the secondary side DC link capacitor, also possible. And then if you consider those inductors as part of the port, then you have an MV type behavior on the secondary side. It only requires an interior closed loop control. All this is to show that MC and MV type behavior are not always unambiguous. They have to be actively established by a decision of the engineer by means of an open loop or a closed loop control. All right, now that we know about the individual ports, let's talk about the interconnections. So basically, I tried to make those two the interconnection variants where you can basically derive every other from. So I called them XPYS, and why is XP? Where I took this terminology basically from battery system, where XPYS means that you can take X individual converter ports, put them in parallel, then you get such a branch here. And then you can take Y of those branches and connect them in series, and you have this structure. If you do it the other way around, you make the series connection first and then the parallel connection, you get those two fundamental interconnection variants. The overall number of the individual ports will be called N, and it's obviously X times Y. Because of the sake of time, I will only talk about the first interconnection variant now. Now I basically took the MC type equivalent circuits and put them in this XPYS structure. So you end up with this equivalent circuit of the interconnected converter port. And now the question is, what are the state variables in this system? And basically making a parallel connection of capacitors doesn't make any difference. But the series connection of capacitors actually adds states. So what you can do is take the individual voltage here and select them as state variables of the system. However, there's one important exception, that if you connect an ideal voltage source to the terminals of the interconnected port, because this ideal voltage source will fix one of those voltages, you can only choose one variable less independently. So in this case, what you can do is take the midpoint voltages, this is one variable less, as state variables. There's also other possibilities, but this is the selection that I went for. All right, so let's briefly summarize. So you have two different types of individual converter ports. There's two different interconnection variants, and there's two load cases with and without ideal source, which makes in total 8 different scenarios. And those 8 scenarios are most useful layer of abstraction, and those 8 scenarios can represent basically any possible interconnected port. And in my PhD, I did the analysis for all 8 of them, but today I will obviously only talk about one. All right, so the question now is, I have this system, how to control it? And the two control goals that I basically defined, I call them internal and external control goals, are first, what you want to do is to keep all state variables in the system controlled and stable. And the external control goals is you want to control the overall power transfer of this interconnected port, as well as the power sharing between the individual converter ports. And if you want to do this, you obviously have to derive state space models. And in this case, the manipulated inputs are all those current sources in the system which you can actively influence. The state variables are the midpoint voltages that I was just talking about. Then the system output I define to be the terminal currents of every single individual port. And because of the ideal voltage source, you don't have any disturbance input in that system, which is already good because it gets us rid of 2 matrices. So now you have to work out all the differential equations of the systems using the capacitor device equations and Kirchhoff's voltage and current laws. And basically this results in the matrices A and C being all 0, which is already nice. So what we're left with are those 2 equations where basically the first one describes how the current sources influence the midpoint voltages in the system, so the system state, the internal control goals. And the second line basically describes how the inputs to the system influence the measured terminal currents, so the external control goals. And if you now look at how those matrices look like using the Kirchhoff voltage law and all of this, you end up with those matrices. I will not try to explain them, but what this basically shows us that every single current source in the system will influence every state variable because this is fully occupied here. And also this means that every current source in the system will influence every single output in the system. So that the fact that those matrices are fully occupied basically shows us the cross-coupling in that interconnection. And now the obvious question is how to decouple the whole thing, how to find this transformation matrix T, which was easy for 2 converters, but now how to do it now. And to remind you, what we did in the last chapter was to apply this transformation to the input of the system. This will be a transformed input with a little wave here on top, and also apply the same transformation to the output. And now you can put this transformation into the state space equations. What you can do first is insert the unity matrix here, which doesn't change anything. And then what you can also do is multiply the second line by T, and then you get the equation in decoupled coordinates. And basically, what you can see in this equation is this structure T times T times T to the -1. May be familiar with some of you. This is basically a base transformation. Maybe you know this still from higher mathematics. It basically takes those very nice and ugly looking matrices which are fully occupied and brings them to their diagonal form. And such a diagonalization can be achieved by if you know the eigenvectors of the system. And using the eigenvectors of the system, you can compose the transformation matrix T. Now, the even bigger question is, what does eigenvector actually mean right now in a physical setting? And yeah, if we look at this equation here, basically it tells us that the rows in this matrix T multiply with all those current sources. So the rows of T define certain current patterns in the system. So for example, if we take the vector 1, -1 and all 0, it will describe a current circulation between those two neighboring individual ports. If we, on the other hand, take this vector, which is all 1 over y, then we basically take the average of all those currents, and this corresponds to the terminal current of the interconnected port that is actually flowing. And this vector, for example, has a very interesting property. If you apply this vector to the transformed matrix here, it replicates precisely, which means that if you use this current pattern in the interconnected converter port, you will directly be able to measure the same current at the location of the sensors without any change or distortion. This means that this current pattern is an eigenvector of the system with the eigenvalue 1 because it exactly replicates. And such an eigenvector I called external eigenvector of the system. But there's even more. If you now look at the matrix B basically describes those current patterns which influence the midpoint voltages or the system states. And what you can find is actually if you multiply B times D, it's actually always 0, which means that the rows of B are containing eigenvectors with an eigenvalue of 0 because they actually vanish here. But what does that mean physically? So I draw here the current pattern, which only changes this first midpoint voltage here. And you can see that because of the amplitude and the direction of those currents, that they basically always cancel out at the location of the sensors. So this means that this current pattern cannot be measured, which makes sense because it charges the capacitors, which are actually before the location of the sensors. So such an eigenvector, which only changes the system states, but cannot be measured at the terminals, I called an internal eigenvector and has an eigenvalue of 0. Now you can build your transformation matrix from this knowledge. So first you have to derive the state space model, already done. You have to identify the eigenvalues. And one interesting thing that you see is that you will always find the eigenvalue 0 with a number that corresponds to the number of system states, which makes sense. And all the remaining eigenvalues will be 1. So if you now can prove that the matrix B really contains those internal eigenvectors, then you can take the matrix B and put those rows in the transformation matrix T. So these are the internal eigenvectors. And now for the external ones, you have to find them. You have to find physically meaningful external eigenvectors. You have to prove that they are really external eigenvectors of D and that they have the eigenvalue 1. For example, the terminal current here, but also in this case, those current differences between neighboring ports are also external eigenvalues. And then you're done. You have a transformation now. Yeah, this transformation matrix will basically make your system matrices fully diagonal, which means that part of the transformed input is now able to influence the system states, but not the output. And the other part of the new input will influence now the output, but not the states. So you have now a perfect decoupling of one interconnected converter port. There's one big question now. This basically only enables you to control one interconnected port because the number of internal and external eigenvectors adds up to the number of individual ports. However, this will be only the primary side, for example, of a DC to DC converter system. So what about the secondary side? You don't have any degree of freedom left, but usually they make an interconnected converter system together. So the big question is, one of those interconnected ports now has to be left uncontrolled. And the question now is which one? And yeah, the question that we have to ask ourselves is how to model the uncontrolled port. And here there is bad news because DC to DC converters are power conserving, or maybe it's good news because they're very efficient. And so on the uncontrolled part of the converter, you always see a constant power source if it's the power output, or a constant power load if it's the power input. And yeah, the bad thing is that those constant power elements are nonlinear circuit elements. So for example, if you take this current fed dual active bridge as shown before. You make the primary side behave like an MC-type port, and you have the power flowing from left to right. Then what you will have is a constant power source element on the uncontrolled secondary side. And now maybe also the uncontrolled secondary side will be now a big interconnection of multiple of those converters. So it will be a system like this. And the question now is, will this be stable if I leave it uncontrolled? And I found the answer to this by using the stability theory by Lyapunov, which is basically designed for nonlinear systems. And if you make a stability analysis of such an interconnected port which contains only power source elements, you will see that such a port is always exponentially stable. On the other way around, if you have constant power load elements in this interconnected port, you will see that this port will always be unstable. So this results in a very simple conclusion. You should always use this eigenvector-based decoupling technique at the power input side of the system, which tends to be unstable. So you have to stabilize it by using the control approach that I've just shown you. And you can leave the output side, the power output of the converter, uncontrolled in this case, because it will always be exponentially stable. Obviously, you have to prove this. I did an experimental validation. I did also measurements for the catenary truck charging onboard charger, which I will not show you today, but they're in the thesis. I basically built this small converter platform here to validate all this. And the topology that I chose was the current fed dual active bridge, because as you have already seen, you can make the primary side behave like an MC-type port, and you can make the secondary side behave like an MV-type port. So you can basically cover all 8 scenarios with this topology. It's 48 to 24 volts. It's rated 200 watts. It uses gallium nitride switches and a switching frequency of 250 kilohertz. To make the whole thing even more compact, I used ultra-compact water coolers by a company that we're friends with, IQ Evolution. They make those 3D printed metal coolers, which are very, very compact. So I built 4 of those converters because 4 is the minimum number that you need for distinguishing the XPYS from the YXP interconnection. And I put them on this control platform here, where you have a FPGA and a microcontroller, which are used to implement all those control loops. And the electrical interconnections can be done on the top side by using those kappa bars, and you can basically make any parallel series interconnection that you like. So the first thing that you need to do now is basically to check whether this MC-type port, for example, on the primary side actually behaves nicely like an MC-type port. So what I did, I implemented the open loop current control for the dual active bridge and saw how can it replicate any commanded current that I put in. And I took a measurement here where you have the commanded current on the x-axis and the actual measured current on the y-axis. And you can see that those are very nicely aligned. And if you plot the error here, you can see that the error is always less than 400 milliamps, which is not perfect, obviously, because it's an open loop control, but it's still nice. And yeah, so the first takeaway is ensuring that this port really behaves like a good MC or MV type is really critical to the performance of the decoupled control. So let's look at the very same example that I derived theoretically now in praxis. So this will be now the XPYS, or in this case, the 2P2S interconnection of the 4 converters that I have. And the single state variable in the system will be the midpoint voltage here. And if there's only one internal eigenvector controlling the midpoint voltage, there will be 3 external eigenvectors, which are the terminal current here and the current differences between the neighboring ports. And because I now used 4 eigenvectors of the system, I have to leave the entire secondary side of the thing uncontrolled. Now the transformation matrix looks like this. So basically the first line is the internal eigenvector manipulating the midpoint voltage. The second line is the terminal current, and the remaining 2 lines are the current differences between neighboring ports. And now basically this is how the system looks like in a block diagram. So because of using this transformation matrix, the system here is fully decoupled. The midpoint voltage can be taken as a measurement. and used in a closed loop voltage control. And this closed loop voltage control acts on the internal eigenvector here. And then I have the three external eigenvectors, the terminal current and the difference of the two of neighboring ports. And for this, I basically didn't use a control loop because the open loop control was already good enough. So the error was quite low. So I didn't really need a closed loop control here. Obviously, what you can do is take all those measurements and also put in here closed loop current control. That will also be fine. But in this case, I only went with open loop. All right, let's take a look at the results right now. So on the primary side, I had a DC link voltage of 60 volts. So 30 volts is the perfect midpoint. And now I used several step changes on the control inputs. So for example, here I set the terminal current from 2 to 4 amps. And in this case, you can see that the step change here in the terminal current is done quite nicely, but the midpoint voltage is basically not affected, which is precisely what you want. You want those variables to be decoupled. Then, for example, I changed this current difference between neighboring ports once, and you can also see that this step change is done quite nicely, that it will not affect the terminal current and it doesn't affect the midpoint voltage. Then also you can obviously change the reference for the midpoint voltage, which is now this closed loop voltage control. And then you can see that the step change is quite nicely followed here by the midpoint voltage, but the terminal current is not affected. So also those variables are fully decoupled. And finally, if you do the step change back from 4 to 2 amps, you can basically see the same. Yeah, finally, the midpoint voltage is decreased again to 30 volts. And yeah, basically this shows you that this eigenvector-based decoupling approach almost perfectly removes all those cross couplings in the system, and you can now influence every variable separately. I didn't talk about the last line of this graph. And this basically shows the secondary side DC link voltage of one of those converters, which is purely uncontrolled. It's that uncontrolled power source circuit, basically. And what you can see is that those transient that I caused by the very steep step changes of the power transfer, that this really, those disturbances basically decay quite nicely. And this basically shows that the stability analysis by Lyapunov that I did for the uncontrolled port really, in this case, I have an exponentially stable secondary side. All right, so maybe let's briefly summarize. The goal was to do a generalized control methodology that should allow a fully independent and decoupled control of all variables in the system. I think by using this transformation matrix approach and the eigenvectors in the system, this can be nicely done. It also should cover every possible interconnection variant. And by using the XPYS and the YSXP, this is basically also true. You can derive every other possible interconnection variant from those two. Then also the approach should be very independent of the DC to DC converter topology and its operating principle. And this has also been achieved because by using the MC and MV type equivalent circuits here, basically this introduces a nice layer of abstraction to this theory, which means that any DC to DC converter topology that you can think of, you can make them behave like one of those two circuits. And also, the methodology should have global and large signal validity. And by using the Lyapunov stability theory, I was also able to have a stability proof which does not rely on a small signal modeling or a linearized model, because power electronics is always a large signal business. And also this has been achieved. And obviously, I validated the whole approach experimentally. So let's maybe conclude with an outlook. So there's obviously much to be done in the future. It should be applied more widely to gain further research insights from a more widespread application. And it would be particularly interesting to explore the limitations of that control approach, for example, with respect to how good this MC and MV type report could be realized. Also, I didn't consider any parasitics in the system, but you have those because of those copper bar interconnections, for example. I basically relied on the fact that those energy storages will be so high frequency in a so high frequency region that they will be way beyond my control bandwidth, but it will still be nice to see how do parasitics in the system influence the whole thing. And then finally, I assumed all converters to be exactly the same, but it would be nice to see how do component mismatches and converter mismatches influence the whole thing. Most likely, they will reintroduce some cross couplings, and yeah, you basically have to see how to deal with that. And one very interesting point will be the bidirectional operation of such a system, because as I told you, you have always to control the input side of the system to keep it stable. So if you at some point reverse the power flow, you have to do a switch over from that decoupling technique from one port to the other port, and it would be very interesting to see how the dynamics of this switchover really can be realized without making the whole thing unstable in that transition. And then there's more theoretical questions. So for example, if you have integral controllers in your decoupled control, how does anti-windup actually work in decoupled coordinates? And even some more generalized question, can the whole thing be expanded to multi-port topologies, for example? And also, could the same approach be used in entirely different areas of power electronics other than galvanically isolated DC to DC converters? So with this, I'm at the end of my talk. I thank you all for your attention. I'm excited for your questions.